Hello friends, welcome to the live session of the NOC, the NPTEL online certification course on welding of advanced high-strength steels for automotive applications. So please ask your questions if you have any doubts regarding the lectures I've recorded and then broadcasted in the course material. So please ask your doubts in the live chat session. I also received a few questions from some of you. So we'll also discuss about that. And then we'll clarify the doubts so far I have received. In the course of this live, we'll also discuss the assignment questions and answers. Right? So we'll begin with some of the questions what we received so far through our Google Doc forum. The question is from Manivel Muralidharan. He's a faculty. Thank you for sending this question. It's very interesting question you asked. In this case, in assignment 3 in question 8, so I asked a question about the effect of welding current on the metal transfer. So the exact question reads like this. When the welding current is increased above spray transition current in Gmaw, so what happens, right? So the options I gave are droplet transfer occurs mainly by gravitational force. And that's the answer, the option A. Option B, drop spray transfer occurs. And option C is short circuiting occurs. And option D, severe spatter occurs. Okay, so the best answer for this question is drop spray transfer occurs. Okay, so the question what Dr. Manivel Muralidharan asked, when increasing welding current, both spray transfer and spatter occurs, which is not really correct. I want to clarify this and how to answer for this. I'm having doubt in distinguishing these two, whether there is a difference between spatter and severe spatter. If it is the case, what range of current at which severe spatter will occur? Okay, so the answer for this question is the drop spray transfer occurs. And if you recall the lecture on metal transfer I gave you in GMAW in week 3, so I drew a list, the graph with respect to sorry about that. Yes. So the droplet diameter and the transfer frequency. As a function of current, this is welding current. In amperes I gave. And I showed an example graph for welding 1.2 mm low carbon steel weld, low carbon steel filler. In agar atmosphere. So when you increase the welding current, the droplet diameter decreases as a function of welding current. So meanwhile, you also increase the droplet transfer frequency. Okay. So ideally, after reaching a critical current value, the droplet transfer changes from globular transfer, which is happening at lower current, to spray transfer, isn't it? So the change in transfer mode from globular or rippled globular to a spray transition is happening at a critical current level. That current is known as spray transition current. So just above the spray transition is most widely used current rating for GMAW, because that is the current at which you achieve a spray transfer in a simple drop mode. So that's known as drop spray transfer. So in this case, you have a droplet detached from the electrode tip with a diameter similar, equal to the filler diameter. And you also achieve a reasonably high frequency of transfer compared to the globular transfer. And droplet diameter is smaller than what you detach during globular transfer. Okay, because the main transfer force that actually aids the transfer upon spray transition is the Lorentz force, the electromagnetic force. Because you can achieve the high Lorentz force by increasing current, you can detach a droplet in smaller volume, smaller size, and that transfer is aided by the high Lorentz force. Okay, so when the current is increased just above spray transition current, so you have a dropped spray transfer. So if you keep on increasing current above the spray transition, so what happens then? The Lorentz force that is formed in the droplet becomes extremely significant, and droplet diameter decreases. Okay, droplet diameter, which is detached from the electrode tip, decreases significantly. So you would end up transferring the droplet not as a single free flight droplet, whereas the droplet diameter is so small, you can't distinguish the droplet, individual droplet at all. So it will be continuous spray, right? And continuous spray, we term this as a jetting spray. Okay, where the current is increased several amperes higher than the spray transition current. So in 1.2 mm low carbon steel, the spray transition can happen, say, 200 amperes when you have a continuous DC in electro straight polarity. So whereas if the current is increased more than 300 amperes for this filler wire, and you will end up getting a jetting spray. Okay. And jetting spray happens because the droplet diameter is so small and you can't distinguish a single droplet. And because of continuous detachment of a droplet, and you have a jetting spray, and the increasing current leading to the enormous Lorentz force generation, and that could lead to a magnetic field generated in the droplets and the sprays that are detached from continuously from the electrode tip. And this the enhanced Lorentz force with the magnetic field that is developed by these Lorentz force can lead to a deflection of these sprays continuously in and around in the arc. So the plasma spray, plasma pressure inside the arc, Lorentz force increased by the increasing current, and the magnetic force, magnetic field that is generated in the droplet would all lead to deflection of the droplet, and in some cases it may also lead to explosion of these droplet that is detached at higher amperage. If you reach such a state where the Lorentz force, the magnetic field that is generated, it is so high, and the pressure inside the droplet can lead to the explosion of the droplet, and that is what is known as spatter. Okay. And that happens especially when the current is increased to much higher than the spray transition. So when you say that spatter happens, that means that you already have unstable droplet detachment. So you are detaching in a much smaller diameter, and that you can't distinguish the individual droplet, and it is like in a continuous spray transfer. It is like opening a tap of water. If you open very slowly, you will have a stream of very nice flow. If you open a tap much more, you see a jetting of water sprayed, and then you see a turbulence in the flow. And imagine you also have an enormous amount of Lorentz force induced inside the this spray, plus the magnetic force that are generated by the increasing Lorentz force can lead to unstable the pressure creation inside the spray, and that lead to the explosion of the droplet. That's what is known as spatter. So the severe spatter happens so when the current is increased much higher than the spray transition current. So the answer to this question is what I asked. When the current is increased above the spray transition, the first thing will happen is the spray transfer. Okay, so in order to have a spatter and severe spatter to happen, severe spelling. So if a severe spatter to happen, So then you need to increase the current to much higher than spray transition, right? So that's the answer to your doubt. So the straightforward answer, the best answer for this question is the drop spray transfer occurs. In order to achieve a severe this pattern, so you need to increase the current to much higher than the spray transition. Okay, so that I hope the answers your question. So we'll start discussing about the quiz questions, starting from the quiz 1 or assignment 1. Before that, there is another query which we received in a Google Doc from Mr. Narasaya. His questions are to do with the properties of ice and steels, but it is not clear what he really wanted to know about the properties of ice and steel. I presume he wanted to know more about the mechanical properties of ice and steels, which we already covered elaborately during our first week course. And if you need further information, and you can always welcome to contact me, and I can share some literatures. And of course, you can also refer the reference books initially I indicated during my first week lectures. And there are a lot of literatures available even in open source. And if you find difficulties in identifying those literatures, please drop an email either in forum, and if forum is closed, you can also drop an email anytime to me. I'll share the literatures to you. Okay. So we'll move on to the assignment questions. If there are no other questions through the forum. So the assignment 1 in the first week, and almost most of you have done well. In fact, I really appreciate all of you. Some of the questions are really testing. I know that, but we wanted to keep it like that, so that you put some more effort in answering these assignment questions. If you have followed the videos very carefully, also the reference books I specified, and it's easy for you to answer this really. And what I formulated the questions, the exact statements I used in the videos. Okay, so nothing else. So had you followed my videos, lectures, and this must be easy for you to answer. So we'll discuss it in then and there. If you receive any other questions in the live stream, we'll also take it up. So the assignment 1, and if you want, you can also refer the NPTEL portal. Okay. The assignment 1, the first question is on silicon and aluminum additions. So those are the most common alloying additions we do it for trip steels, right? The question reads, silicon and aluminum additions in steels retard cementate formation. How? Well, that's the answer I expected. And they retard the cementate formation because the low solubility of these elements in cementite, right? So because when the cementite has to nucleate, and the silicon and aluminum atoms will be pushed out, okay, from the nucleation sites of cementite, right? And because of low diffusion rate of silicon and aluminum, and it's difficult kinetically. Therefore, the cementate precipitation is retarded. And so why the cementate precipitation retarded? Because the cementite lattice cannot hold silicon and aluminum. Okay, so it has to be pushed out. So the low solubility of silicon, aluminum, and cementite is the main reason why these elements retard the cementite formation. The second question, the strength of interstitial free steel is generally increased by, so the strengthening mechanisms. Okay, so what are the common strengthening mechanisms? And in 2 cases, we can increase as per this question by precipitation hardening and by addition of microalloying additions. Both are same, right? By adding microalloying elements, what are the microalloying elements we have and commonly added in steel is vanadium, niobium, and then titanium. Okay, and these are all carbide and carbonitrate forming elements, so they form precipitates. Okay, so precipitation hardening is the most commonly used strengthening mechanism for interstitial free steels to increase the strength level. So the IFHS, so recall my lectures, the interstitial free high strength steel is actually microalloyed. Right, so the vanadium, niobium, titanium forms vanadium carbonitrates, vanadium carbides, or the mixture of vanadium, niobium, and titanium carbonitrates. Okay, so one question has come from the live stream from Mr. Bhargav. Which parameter is most important to control spatter? Okay, so there is again, so it is a very good question. The process stability determined by the various factors. For example, the R characteristics, okay, and also the weld preparation, the surface preparation. So you also have the stability of the power source. So in order to control the spatter formation, the important factor immediately you can look at is the droplet transfer behavior. Okay, so droplet transfer behavior is very critical for the spatter formation. And I talk about the 5 forces that contribute to the droplet transfer, right? The 3 forces that aid the droplet transfer, 2 forces they always oppose the droplet transfer. So the forces that aid the droplet transfer is gravity when you do a downhand welding. So most of the cases we do downhand welding, right? And then the other force which aid the droplet transfer is the plasma drag or aerodynamic force. Okay, and then the other force which the aid the droplet transfer, apart from gravity and the plasma drag, is okay. So I'll get back to that. Gravity, plasma drag, surface tension. Okay, surface tension is also very important parameter which controls the droplet transfer kinetics, and then the vapor pressure. Okay, so the gravity plasma drag, which always aids the the droplet transfer. Okay, the surface tension, vapor pressure, okay, they always oppose the droplet transfer. And apart from these 4, the important force that controls the droplet transfer kinetics is the Lorentz force. Okay, the gravity, plasma drag, which is all the process specific. Suppose if you fix the process, okay, you choose a sealing gas, you choose a given filler diameter, you choose the velocity of shielding gas, what you use, and the mode of welding, whether you have downhand welding, up-hand welding. So once you choose the welding process, these forces are more or less fixed, right? If a material is fixed, material composition is fixed, surface tension is also fixed. Okay, so be it if you use a bare GMAW or the flux coated wires, so the surface tension is determined by the electrode composition. Okay, and the vapor pressure is again created by the evaporation of the well pool. This vapor goes up and then they pull the droplet or push the droplet in its position. So when you fix the material, this is also fixed. Okay, so the other force which controls the droplet transfer is the Lorentz force. Okay, so that's the electromagnetic force which aids the droplet transfer. Most of the cases it aids. So assume that it aids the droplet transfer. So now, as I had explained during the metal transfer, the drop spray transfer and the jetting spray, the kinetics and the size of the droplet changes as a function of current. And this change, what we observe here, is mainly due to the change in the Lorentz force. So at higher currents, okay, if your current is much higher than your the droplet spray transfer current, the amount of Lorentz force generated is extremely high, leading to explosion of the droplet. And this explosion is also aided by the vapor pressure, because if you have a lot of fumes generated, if you have material with a very high surface tension, and it is difficult for droplet to transfer for a given current, and you start accumulating the droplet to a larger volume, plus the Lorentz force and the vapor pressure which is coming up from the whirlpool would cause the explosion of the droplet. Okay. So first thing, if you see a lot of spatter in your weld, look at the current level you're operating, try to minimize that. Then you need to see that you still above the spray transition, so that you can get a good productivity. The other thing you need to look at is the fumes, the amount of vapors you generate, and if that is really high, then that will also influence the stability of the droplet you transfer. Okay, so the moment you see there's a lot of spatter is happening, look at your current. So what current you are operating, try to minimize that. Okay, and then you can look at the material specific parameters like surface tension, which is determined by composition, and the vapor pressure, the fumes that are generated, right? So, and these three factors, you can look at it. The first thing you need to see, as I said, the Lorentz force, which is controlled by the current. Okay, so I hope the answer is okay with you. So we'll continue with the assignment. So we looked at the assignment 1, questions 2, and we'll move on to question 3. Compared to silicon, aluminum, and steel, compared to silicon, aluminum and steel is, so aluminum is very strong oxide former, but unfortunately, it is very poor solid solution strengthener. So the strength increase by adding aluminum, it's not that effective compared to addition of silicon. So that's why in aluminum containing trip steels, we also have to have some other alloying additions to achieve the strength level equal to the silicon based trip steels. So which I already discussed in detail. So sometimes we also add phosphorus, because phosphorus also does the job by increasing the strength due to solid solution strengthening, and suppressing the cementate formation. But we looked at in detail the role of phosphorus, how it embrittles weld, right? So question 4 on assignment 1. The enhanced ductility of dual phase steel is primarily due to the formation of mobile dislocation of the interface. So when you do a trip steel heat treatment, I already explained, you form martensite in amidst ferrite matrix. There is a volume accommodation leading to formation of mobile dislocations at the interface. Okay, that gives the improved ductility. And we also have a two-phase microstructure. So one is really soft, one is hard. So obviously, the ductility of the ferrite matrix is much higher than the martensite matrix. So when you're deforming it, the stress, the load is partitioned to the soft ferrite, leading to improved ductility. And the question number 5, so boron increases the hardenability of steel because the answer is it suppresses ferrite nucleation. How it suppresses ferrite nucleation? Because the solubility of boron in ferrite is also very low. Same as how silicon aluminum suppresses cementate formation. So question number 6 in assignment 1. When hot forming steels are deformed when the temperature is fully austenitic, right? So in order to avoid all the complexities in the intercritical region and to achieve fully martensitic microstructure, so we always aim to increase the temperature above the A3, the austenite formation temperature, austenite completion temperature while heating. So we can achieve 100% martensitic microstructure upon forming when you quench the formed component. So question 7, the enhanced uniform elongation in trip steel is due to the stress-induced transformation of austenite to martensite. Okay, so I already addressed this question in the forum. Someone asked about how does this stress-induced transformation of austenite to martensite increase the ductility. So I already explained various mechanisms. So one of the mechanisms which is most accepted is when you transform the austenite, retained austenite to martensite, there is a volume accommodation leading to generation of mobile dislocations at the interface. So that can increase the ductility significantly. Then in the question 8 in assignment 1, the austenite is retained in trip steel upon heat treatment by two ways, by carbon enrichment in austenite and by incomplete austenite to binary transformations. Okay, so both are interrelated. So the answer here is the carbon enrichment austenite, the incomplete austenite to binary formation, and then we can also get the answer C, retardation of cemented precipitation. So cemented precipitation also leads to the carbon enrichment in austenite, which is untransformed. So you can say that incomplete austenite to binary transformation, which already explained the incomplete reaction phenomena, right? So, and then the question 9, the microstructure of components made of hot forming steel contains. It's obviously, so after forming, we aim to get fully martensitic microstructure. And the assignment 1, question 10, when undeformed austenite transformed to lower bainite. So when the austenite, which is non-transformed, transformed to lower bainite. So lower bainite, so the cemented precipitation, and we can also expect in between the ferrite laths. Okay, so intra-lath precipitation of cementite. Okay, good. So that's the assignment 1, and yeah, you guys have done reasonably well. I didn't expect that, because given the difficulty level of the questions, so I'm really happy about that. Okay, so is there any question? So we'll move on to the assignment 2. If there are any no other questions. So meanwhile, we can also erase this, or we move on to the next page. Okay. So the assignment 2, the first question. So what is allotropic phase boundary? Okay, so again, I'll explain during my lecture. So the allotropic phase boundary is also known as T0. Is defined as the carbon concentration at which both ferrite and austenite have same Gibbs energy, and the carbon concentration of ferrite and austenite remains the same. Okay, so the carbon concentration of ferrite and austenite at which both phases have same Gibbs energy. So the carbon concentration should also be the same, and the Gibbs energy of both phases will be same. So that is the maximum common limit upon which austenite gets stabilized. Okay, so for example, if the carbon concentration reaches the T0 allotropic phase boundary carbon concentration, and after that, the austenite can transform only by diffusionless manner. So it can transform to martensite, or because of increased decreased MS and MF temperature, it can be retained to room temperature. And if you want to transform that, you need to quench it to sub-zero temperatures. Basically, you need to cool it below MF temperature. So why? Because the carbon decreases the MS and MF temperature, right? So if you enrich the carbon, enrich the austenite in carbon, the MS and MF decreases. So the second question is heat generation resistant spot welding is mainly dictated by. So I also explained elaborately during this course the contact resistance of the interface between the sheets to be welded, isn't it? Yeah, so that is the rate controlling resistance in generating heat in resistance spot welding. So question 3 in assignment 2, when electrode force in resistance spot welding increases, what happens? Contact resistance decreases because you are giving more force. Okay, so then obviously contact resistance decreases. Okay, good. And then the question number 4, the preheat time in enhanced resistance spot welding thermal cycle is to, so it is to reduce the cooling rate upon welding, and it also reduce the temperature gradient before the onset of welding. And the question 5, the Imax and resistance spot welding, again, so someone asked this question in the forum as well. The Imax is nothing to do with the equipment. Okay, so Imax is the current at which expulsion of melts occur. Right? The 4 by square root of thickness is not Imax. That is the ideal nugget diameter we can have. And then assignment 2 question 6, weld time of resistance spot welding is. Okay. So there is one question from Mr. Nazir Mohammed before we see this question number 6. Can we do MIG on spring steel? If yes, then what gas? I presume you asked for gas, shielding gas should we use? To answer this question, it is again beyond the syllabus, what we intend to do in this course. Nazir, I advise you to contact me because we need to discuss it elaborately. So we need to look at what filler wire you want to do. It is not that straightforward. So we can do with a dissimilar filler, but 1% carbon is extremely high carbon, right? And spring steel, if you're doing a MIG, we'll have to use a low carbon filler, but again, yeah, so if you are doing a spring steel, I don't know, we need to look at the joint, the geometries, thicknesses of the steel plate, what you're going to use, because that will determine the constraints, the stress evolution, and we need to discuss elaborately. Yeah. So I can't really give a straightforward answer unless I know your the weld geometry, how many passes you want to do, thickness, the filler wires, what you want to do that, and what weld metal property you want to achieve. But 1% carbon based material. So there are other methods you can use to weld. So MIG, yeah, we'll have to see. Okay, so we'll go back to that assignment 2 and question 6. Weld time of resistance spot welding is directly proportional to the thickness of the sheet. The higher thickness, longer you need to weld because the mass effect I told you in the class. On the 7, in assignment 2, question number 7, in full interface failure of resistance spot weld, the plug ratio 0. Because what is a full interface failure? We just open the weld as it was before welding, right? So the nugget diameter over, for example, plug ratio is the plug size upon testing by the weld nugget diameter. If there is no plug size, if it is 0, obviously plug ratio becomes 0. Okay. So we'll move on to the question number 8 in assignment 2. The deterioration of copper electrode life while welding galvanized steel is mainly by the zinc diffusion. Right, so galvanized layer is a zinc containing layer. The copper readily forms the copper zinc alloy. You can say the copper zinc is commonly known as composite alloy is known as brass. So the brass formation is the main reason you have deterioration of copper electrodes. Okay, so you don't melt the electrode, or oxidation of copper is also not going to happen because the electrode temperature seldom go higher, because you also have water circulation inside the electrode. And diffusion of copper to steel, so I put this deliberately, and the copper diffusion of steel is extremely sluggish. Okay, it's never is going to happen. So the answer for question 8 is the diffusion of zinc to the electrode surface. So assignment 2, the question number 9. When the ultimate tensile strength of the steel increases, failure of resistance part will. So obviously the high strength material means you also have higher alloying elements, more carbon, right? So then the failure mode changes from full plug to interface failure. Okay. The assignment 2, question 10. Generally, alternating current is preferred for resistance spot welding. So reason why we use the alternating current to overcome Peltier effect, right? So what is Peltier effect is opposite to Seebeck effect, and we discussed that during our class, right? So refer the video. So when you have a direct current, so dissimilar junctions kept at different temperature would generate an EMF. That's the Seebeck effect. And when you have dissimilar junction using an EMF, obviously these two dissimilar junctions would always be in different temperatures. Okay, so that's a Peltier effect. So in order to overcome that, either need to change the polarity or using alternating current is the best choice. Okay, so this is assignment 3. So if there are no other questions in the forum, so we'll move on to the assignment 3. Assignment 2 is done. So assignment 3, this is on mostly laser and arc welding. So the first question of assignment 3 is, which mode of laser beam welding is preferred to achieve the increased depth of penetration? So obviously the keyhole. So I also showed a lot of videos which we recorded using laser beam welding, right? So the keyhole stability is a function of vapor pressure during overlap welding. So we discussed in detail. So the best mode of achieving increased penetration is through keyhole formation. The question number 2 in assignment 3, the shape of the weld pool in laser beam seam welding is generally a teardrop. Okay, so teardrop shape. Sorry. So that's the most commonly observed. This pen is very tricky to write. Okay, so the question number 3 in assignment 3 is recoil pressure in the keyhole of laser beam welding is due to. So recoil pressure is like an vaporization of the melt. Okay, the principle by which the rocket works. So the vapor is actually going up, and it's creating a downward pressure, leading to the generation of recoil pressure in the keyhole. Assignment 3, question 4. So which one of the following controls the stability of the keyhole during laser welding of galvanized steel in overlap configuration? So this question related to the videos I showed you when we are doing galvanized steel welding in overlap configuration. The zinc vapor determines the keyhole stability. So the vapor pressure determines when you are welding on a galvanized steel the keyhole stability. Then assignment 3. So yeah, you may also ask if you have questions meanwhile in the assignments. Please drop a line in the chat window. So we'll try to catch it up. And the assignment 3, question number 5. Process efficiency of arc welding process is determined by efficiency. It's always determined by the heat transfer from an arc. Okay, so how much heat is actually transferred from the arc to the workpiece, that determines the efficiency. And efficiency can also change if you change the polarity. If you're using positive electronegative, the polarity would also change. So you always have efficiency changed by the efficiency by meaning arc energy. Okay, how much arc energy is going into the workpiece, that determines the efficiency. So in all the cases, the process efficiency is determined with heat transfer from the arc. And question number 6. Droplet detachment in consumable electrode welding is always opposed by. Okay, so I just explained in while explaining the doubts from one of the students. So detachment is always opposed by the surface tension and vapor jet forces. Plasma jet force and gravity, they aid the droplet transfer, especially gravity aids when you're doing downhand welding. If you're doing uphand welding, it also resists, opposes. And the question number 7. When stick out length increases, melting rate of consumable in Gmaw. So melting rate is directly proportional to the stick out length. Okay, so the equation for melting rate is m in meter per second is alpha I plus beta L I square by pi r square. So this is the joule heating of the electrode. And this is coming from the heat supplied from the arc. Okay, in this case, the L is the stick out length. So more the stick out length, more you melt. So when the stick out length increases, the melting rate of consumable in Gmaw also increases. The assignment 3, question 8. When the welding current is increased above spray transition current in Gmaw, that's what we discussed in detail, the dropped spray transfer occurs. And assignment 3, question 9. In cold metal transfer welding, primary metal transfer mode is, so that is a very straightforward question, because cold metal transfer welding is developed with respect to the short circuiting transfer. And assignment 3, question 10. In pulse Gmaw, which transfer is promoted? Okay, drop transfer is promoted. Okay, in pulse Gmaw, the heat input is generally much lesser than you have a constant current MIG Gmaw, and mean current is decreased. You will never get a jetting spray in pulsing because the current is not constant. Okay, so with that we conclude first 3 assignments. We can't discuss assignment 4 because it's still open. So if I tell all the answers, you guys can answer it very easily. And hopefully you'll get another out of 100. So we'll keep the assignment 4 as of now out of the discussion. And if you have any questions on assignment 4 as well, drop by on the forum. Please use the forum for asking questions. If you reply to the emails, it goes to my inbox. And I don't check my email inbox for this course. So I do regularly check the discussion forums and I answer. So make sure that you ask the questions in the forums. And if you want to write to my personal email inbox, you are free to do that. You can use my homepage to identify my email ID and drop an email. I can help you with various problems if you have. Provided if it is not really time consuming. Okay, so if you have any difficulties in your daily life with respect to welding, you're always welcome to contact me. I'll try to help you with that. I would reply to your emails if it comes to my inbox, definitely. But yeah, please don't expect immediate response. I would definitely reply. If you don't get any reply, that means that I didn't get your email. Okay. So with that, we'll try to conclude this. If there are no other questions, we can wait for a few minutes. Otherwise, we'll wind up this live session. So please feel free to ask some questions. Otherwise, I wish all of you very good luck. All the best for your studies, for your work. We'll try to float another process course, welding process course, which can give much more physics of welding processes in greater details. That will be a longer course than the 4 weeks course what we offer now. I'm looking forward to seeing all of you there as well. We'll wait for a few minutes for your questions, otherwise we'll wind up. So meanwhile, please refer the literatures I referred in my earlier lectures videos. So those are some of literatures you can always refer, especially the World Auto State Body literatures. They do a lot of work with respect to commercialize advanced ice and steels. Some of the basic literatures and you can find in ULSAB AVC. ULSAB AVC is ultra light steel auto body advanced vehicle concept. You can just Google and you find a lot of literatures. And this ULSAB is set up by all the steel manufacturers in the world, and they do carry out literature surveys and the basic information about advanced ice and seals you can find in those forums and the database. Those are freely available to download, and then make sure that you read them. And they also update their literature database very regularly. Yeah. Apart from that, you're also most welcome to answer the ask questions. Yeah, to me by email or by any other way. Good. So thank you. With that, I see that not many questions coming up. We'll wind up. Thank you.